Welcome back, everyone. I'm Jordan Giesecke, and this is The Limiting Factor. This video will be the final and quintessential video that will wrap everything up from my original Battery Day series, taking into account everything we've learned in the past 6 months and how my thinking has progressed. For those who missed the original series and want to go deep on the technology, I'll link those videos in the description. Before we begin, a special thanks to Bradford Ferguson of Halter Ferguson Financial and the Patreon supporters listed in the credits. It's the support on Patreon that keeps me grinding away on niche topics. Let's get right into it. At the end of the last video in the Battery Day series, I showed this chart, which might lead you to believe that specific energy is the most important factor for Tesla. This is not the case. In order for Tesla to grow their total production to 20 million cars a year by 2030, they'll need to reduce the cost of their batteries. The average selling price of a vehicle in the US is around $35,000, whereas the average selling price of a Tesla vehicle is around $56,000. Tesla needs to drive down to the $20,000 to $35,000 vehicle price bracket to put their products within the reach of more people. This is the goal of Tesla's Project Roadrunner, which has a cost target of $100 per kilowatt hour at the pack level. Crossing the $100 per kilowatt hour price barrier is taken as a sign that electric vehicles are becoming cost competitive with ICE vehicles without incentives. The cheaper the battery pack, the larger Tesla's market access and the fatter the profit margins. Just 2 years ago, in 2018, Sandy Monroe found that the cost of a Tesla battery pack in the Model 3 was $135 per kilowatt hour. The newest information we have from Sandy is that Tesla battery packs have achieved $110 per kilowatt hour in the Model Y. This $25 per kilowatt hour improvement on an average pack size of 70 kilowatt hours would have reduced the production cost by $1,750 per vehicle. Despite the improvement, that still leaves the battery pack at around $7,700 for the average Tesla on the road today. Tesla will continue to take a multi-pronged approach to continue to chip away at the $7,700 pack cost. The standard range Model 3s in China will use CATL lithium iron phosphate or LFP batteries. These batteries are rumored to achieve $80 per kilowatt hour at the pack level. This would mean that the battery pack in the China-made Model 3 is around $2,100 cheaper than Tesla's cost in the US. The reason why the LFP batteries are so much cheaper than Tesla Panasonic battery cells is that the raw materials used to produce LFP batteries are 1/3 the cost of the materials that go into the high nickel chemistry that Tesla Panasonic uses. Furthermore, the cost of manufacturing is cheaper in China. Why doesn't Tesla switch to LFP for all their vehicles? Energy density. Tesla can only fit so many LFP batteries in the floor of a vehicle because they have low energy density. This energy density limits the range of electric vehicles with LFP battery packs to 250 to 300 miles. Tesla needs a high energy density battery option that will provide ranges of 300 to 500 miles. As a side note, why is Tesla trying to hit 300 to 500 miles of range? Range anxiety is still a real thing, especially for people in colder climates or those in rural areas. Larger battery packs are also one of the best ways to extend battery life and increase charge rates, because a larger battery pack has more spare capacity. Lastly, in order for EVs to dominate, they need to take every excuse away from their critics. The range argument needs to be blown out of the water. High energy density batteries are usually made with nickel, which is more expensive than the iron in LFP batteries. How can Tesla hit the $100 per kilowatt hour price target with a high nickel chemistry? Let's take a closer look at Project Roadrunner, starting with Elon's comment about the future possibility of Terafactories. I think Tesla fully intends to build Terafactories. However, I don't expect that the version 1.0 Roadrunner line that we'll see at Battery Day will be able to support Terafactories. With that said, if a Terafactory is the end goal, crunching the numbers on a Terafactory may provide insights into Battery Day. Giga Nevada currently produces around 35 gigawatt hours of battery cells per year. When complete, it's expected to produce 150 gigawatt hours of cells per year. There are 4 ways to scale from 150 gigawatt hours per year to 1 terawatt hour per year. The first is to increase the size of the factory. The general trend for the size of Tesla's plots of land is getting larger. The plot of land for Giga Texas will be even larger than the plot of land for Berlin, and comparable in size to Giga Nevada. However, these gigafactories will be producing not just the cells, but also the rest of the vehicle. Giga Nevada and Giga Texas also appear to have significant amounts of land devoted to preserving nature. The outlier is Shanghai, which is smaller, but at this point, the factory is sourcing cells rather than manufacturing them. With that in mind, let's assume that the size of future battery manufacturing operations will remain the same as Giga Nevada. The second is to increase the specific energy of each battery cell coming out of the factory. I still expect, at minimum, a 20% increase in specific energy for the battery cells that Tesla will unveil at Battery Day. A 20% increase in specific energy for a Giga Nevada-sized project, which is 150 gigawatt hours per year, would result in 180 gigawatt hours per year. A 20% specific energy improvement is a conservative expectation. However, even a 30 to 40% specific energy density improvement is a drop in the bucket compared to the hundreds of percent improvement needed for a Terafactory. We'll stick with 20% to be conservative. The third way to bridge the gap from gigawatts to a terawatt is to decrease the amount of space each line takes up in the factory. Maxwell technology is able to reduce the space taken up by the electrode coating process to 1/16 that of a wet slurry process. However, the electrode coating process is only about 20% of the total battery factory floor space. The space savings from the tabless electrode patent, which we'll get to later, is another 5% space savings. Building on the 180 gigawatt hours, these compact lines would allow for 240 gigawatt hours in the same footprint. The only other way to make up the gap between 240 gigawatt hours and 1 terawatt hour is to speed up the lines. In other words, if Tesla intends to build a Terafactory with Maxwell DBE lines using the same size footprint as Giga Nevada, our calculation would be 1 terawatt divided by 240 gigawatts. This means that the Maxwell lines would need to achieve at least 4.16 times the output of the Panasonic manufacturing lines at Giga Nevada. We'll call it an even 4x. The Panasonic cell lines at Giga Nevada each currently produce roughly 2.7 gigawatt hours per year. Multiply that by a 1.2 specific energy density increase at the cell level, and 4 for the line speed increase, and we arrive at 13 gigawatt hours per line per year. In other words, in the future, 1 Tesla cell line may be capable of producing over 1/3 the entire output of Giga Nevada, which has 13 cell lines. No wonder they're calling the battery lines Roadrunner. In the last Battery Day video, I included an estimate by George Bauer of Inside EVs. He estimated that Tesla could save up to 20% at the pack level with lines that were 4 times faster and with a new type of cell-to-pack technology. I don't think Tesla will use the type of cell-to-pack technology that George has suggested. However, I do think that Tesla will switch to a basic cell-to-pack design with Roadrunner. If Tesla's current battery pack for the Model Y is $110 per kilowatt hour at the pack level, a 20% cost reduction would blow past Roadrunner's price target to hit $88 per kilowatt hour at the pack level. If Maxwell DBE is at the front of the manufacturing line blasting out cells, how would the rest of the battery line keep up? After the electrode rolls come off the DBE lines, they need to be cut and stuffed into battery cells as fast as bullets coming out of a machine gun. This is where Tesla's tabless electrode patent comes in. One of the trickiest and most error-prone parts of battery manufacturing is welding the battery tabs to the electrode. The tabless electrode patent may remove the need for welding by using the entire edge of the electrode as the battery tab. In the tabless electrode patent video, I suggested that removing the welding from the production process would reduce the cost of the battery by 5%. We'll keep this 5% in the bank for now. After the electrode roll is inserted in the cell, it needs to be filled with electrolyte at high speed. This is where Tesla's acquisition of Highbar comes in. Highbar specializes in high-speed electrolyte filling machines. Finally, the cell is capped off and run through testing and aging processes before it's incorporated into a battery pack. Battery pack manufacturing can be sped up by what I call basic cell-to-pack technology. This is exactly what it sounds like. Battery cells are fitted directly into the battery pack. This is not the way Tesla battery packs are currently manufactured. For all of Tesla's current vehicles, the cells are built into modules, which are then built into the pack. Modules were originally used in the early days of the Tesla Roadster to accommodate manufacturing issues. If too many battery cells in a module failed, Tesla wanted to be able to replace one module instead of the entire pack. Since then, both cell and pack manufacturing have become more reliable. The battery pack module has remained like a vestigial organ, creating excess weight and providing no utility. It's time for the module to go. This will decrease pack weight. It will also simplify and accelerate manufacturing. In prior videos, I suggested Tesla might use advanced cell-to-pack. Advanced cell-to-pack involves building the battery cells directly into the battery pack, like a tray of popsicles, and might allow the ability to combine cell production with pack production in one streamlined process. I'm less convinced of it now. With advanced cell-to-pack, as I described it, cell testing would occur after the pack is fully constructed. Removing and replacing defective cells would be rework. Rework means repeating or correcting a previous step in the production process. Rework is the bane of production lines. I only see 3 solutions to this rework: cell defect rates that are well below industry standards, a cost-benefit that makes up for this rework, or keeping the defective cells in the pack. Keeping the defective cells in the pack would generate excess weight and waste, require binning like microchips, and software engineering solutions to account for the variable pack energy. With that said, there will be synergies with having the cell and pack production on the same line. For example, logistics costs for moving cells between states and even countries will be minimized. I won't make any further adjustment in cost for basic cell-to-pack because it was already included in George Bauer's 20% cost reduction estimate above. In prior videos, I also suggested that Tesla would increase the size of their battery cells to increase production speed and decrease cost. If Tesla increases the diameter of their battery cells from 21 millimeters to 40 millimeters and kept the height the same, this would be a 300% increase in volume. 300% greater volume in each cell would mean 75% fewer battery cell cans, jelly rolls, welds, and electrolyte fills. There are no estimates out there on how much production cost this would save. The research I found indicates it would depend on the overall production process. In previous videos, I noted that a thicker battery might require a better battery thermal management system. I've since settled on plate cooling as the best option. For me, Rimac is the most impressive electric vehicle producer outside of Tesla, and their upcoming supercar will use plate cooling because they found it's more effective. Whether this is cost-effective for Tesla may be another story. However, it does seem like a lightweight and simple solution, and I can't see any showstoppers. Regardless, why is plate cooling so effective? The inside of a cylindrical cell contains rolled-up copper and aluminum electrodes separated by plastic layers to keep the battery cell from shorting itself out. That plastic is not thermally conductive. The table on the screen illustrates just how much more conductive the copper foil of a battery is than some common plastic materials. That is, thousands of times. Plate cooling involves cooling just the edge of an electrode. The electrodes are made of copper and aluminum, which are far more thermally conductive than plastic. In other words, the copper and aluminum are able to wick heat out of the battery cell quickly and evenly. The tabless electrode design may multiply this wicking effect by providing much more surface area to conduct heat. This would be perfect for a Plaid Model S or the Tesla Roadster. Let's take a breather for an interim summary. If Tesla can hit a 4x production speed improvement required for a Terafactory, then we may be looking at $88 per kilowatt hour for version 1 of the Roadrunner line. My view is that this is aspirational, and version 1 will fall short of this. If we drop the 4x production speed improvement and went with a doubling of production output instead, we might assume a 10% reduction in cost instead of 20%. I doubt the relationship is linear like this, but it will serve as a rough estimate. Earlier, we put 5% cost reduction in the bank from the tabless electrode patent. However, the argument could be made that with larger cells and reduced logistics cost from having cell, pack, and vehicle production in the same location, that Tesla might still be able to squeeze out another 5% reduction in cost, allowing us to continue with the 20% estimate George Bauer used, leaving us at $88 per kilowatt hour. What about the chemistry of the cell and how will it impact the production cost? In the original Battery Day series, I suggested several innovations to Tesla's battery chemistry. A single crystal cathode made with 95% nickel and 5% aluminum, a titanium oxide coating, and an electrolyte solution from Dalhousie University. This chemistry could hit at least 4,000 cycles for a 1 million mile battery life while sustaining serious abuse. I also advised this chemistry would increase energy density by up to 20% to hit 300 watt-hours per kilogram of specific energy. I view Panasonic's recent statement as confirmation that my estimates were correct here. They indicated a 20% energy density improvement by 2025. That would increase their current 247 watt-hours per kilogram up to about 296 watt-hours per kilogram. Why would it take 5 years to ramp this new cell chemistry? The single crystal cathode may not be available at the ridiculous quantities and low cost that Giga Nevada needs. The cathode suppliers to Giga Nevada, which are Japanese, may need time to drive down the cost and scale the single crystal cathode material. Single crystal cathode coated with titanium oxide requires a more complex and energy-intensive process. However, they may be able to license a solution. Nano One, which specializes in single crystal cathode, has just signed a joint development project with a multi-billion-dollar cathode manufacturer, but didn't say which company. Nano One said the company was in Asia and outside of China. It could be that Nano One is working with one of the Japanese cathode suppliers to Giga Nevada to bring low-cost single crystal cathode supply online in the next few years. How much more does single crystal cathode cost? According to CATL, their new million-mile chemistry would cost 10% more at the cell level. I'd attribute most of this additional cost to the single crystal coated cathode that's required for the million-mile chemistry. Given that single crystal cathode is relatively new, scarce, and expensive, it's better to use single crystal cathode for Tesla's new pilot line. Tesla's pilot line won't need as much material. It'll be Tesla's flagship battery cell, and the benefits of Roadrunner can help absorb the cost. This highlights an important point. Tesla wouldn't be constrained by Giga Nevada's supply chain and could partner with any supplier. For example, there was a report that said CATL was working with Jeff Dahn's lab to develop the million-mile battery for Tesla. There may be a grain of truth to this. CATL is able to manufacture single crystal cathode, and they might already have the resources to manufacture significant quantities for Tesla's Roadrunner line. Besides the cathode cost of the million-mile battery, it may also require a fully synthetic anode. Jeff Dahn paired synthetic anode with single crystal cathode for the million-mile battery research paper, because synthetic is capable of longer cycle life than natural anode. Synthetic is more expensive than natural anode. Natural averages $8 per kilogram, whereas synthetic averages $13 per kilogram. However, the million-mile battery chemistry Dahn created was an overachiever and actually blew past Tesla's 4,000 cycle requirement. The rumor is that Tesla uses a blend of natural and synthetic anode in the cells from Giga Nevada. This takes advantage of the high cycle life of synthetic, along with the low cost of natural. Given the fact that the million-mile battery chemistry overachieved, Tesla may be able to stick with a synthetic natural blend or even increase the amount of natural anode. This would help keep costs down. Time for another interim summary. If Tesla does reveal a high energy density, long cycle life battery cell at Battery Day, then it will likely add cost to the $88 per kilowatt hour I targeted earlier. CATL's estimate of a 10% cost increase for a million-mile battery chemistry is likely the most accurate information we'll find. Adding 10% cost at the cell level to the $88 per kilowatt hour pack level estimate from above would result in a battery around $97 per kilowatt hour at the pack level. Cost aside, what about energy density? My estimates remain unchanged from the original series, and I'll provide a quick refresher to explain the curve of the chart. If Tesla uses the million-mile chemistry, they would hit close to 300 watt-hours per kilogram. If Maxwell technology allows for larger amounts of active material, this would bring the cell up to 315 watt-hours per kilogram. A larger cell might increase energy density further to 330 watt-hours per kilogram. If Tesla increases the silicon loading by a modest amount, the cell will max out at 340 to 345 watt-hours per kilogram. All of these happening is unlikely. There was a lot of hype around a high-loaded silicon anode a few weeks ago. However, Elon's tweet knocked the wind out of that hype. Silicon is part of Tesla's future, but in a different form than silicon nanowires or nanotubes. But that's a topic for another video. Just a quick addendum here, folks. I had an interview with Shirley Mung today, and one point that she made was that the Maxwell technology allows for a thicker cathode. I actually mentioned this in my original Battery Day series. I threw it out because I didn't think it was possible to do both a thicker cell and a thicker cathode because of the additional heat generation and retention. However, if Tesla can do both a thicker cell and a thicker cathode, the bend of this chart would actually increase up to what Elon suggested in 2018. Let's talk about Elon's comment about Battery Day being mind-blowing. I think he was looking at it from the perspective of someone who knows how difficult it is to make any improvements to manufacturing processes. If Tesla was able to increase production output of battery manufacturing lines by double, that would blow my head clean off my shoulders. I can't emphasize this enough. Battery manufacturing is a well-established process. Increasing it by just 20 to 25% would be mind-blowing. However, on Battery Day, there's a good chance Tesla will unveil the highest energy density, cheapest, longest life battery cells on the market that are also cobalt-free, along with a high-speed manufacturing line. Each of these is an achievement. Bear in mind, if the Roadrunner line truly is a pilot line, it may take 6 months from Battery Day before the pilot line at Cato Road can hit $100 per kilowatt hour. The information on screen is the best I've found so far, and it's compliments of JPR007 on Twitter. Even for an experienced manufacturer like Panasonic, the first year of production typically sees a yield rate of less than 50%. Yield rate in this image appears to be the capacity of the line versus output, which could include a number of factors such as staffing levels, line downtime, cells not passing quality control, or cells that need to be scrapped. This has implications for recycling, which we'll cover in a moment. I think Tesla will be able to ramp more quickly than this because they already have an R&D line in the same building that's probably using the same process but at a smaller scale. This is where they likely got the batteries for the Plaid Model S that was at the Nürburgring last year. As a side note, Battery Day is on the 22nd of September, which is Hobbit Day. Hobbit Day is synonymous with Lord of the Rings. Maybe we'll meet the new Lord of the Nürburgring at Battery Day, the Plaid Model S. I expect the first 3 to 6 months at Cato Road to be choppy and for those cells to be costly. The same is true for other production ramps, such as the Model 3, which was losing money hand over fist for the first year. However, with experience and time and iteration of the cell line, the process will become more streamlined and profitable. For this reason, I don't expect Tesla to build further battery production lines until they have the production process nailed down. It makes sense for the next Roadrunner lines to be built at Giga Texas and to supply batteries for the Cybertruck in late 2021. With that said, Elon has said that some of what relates to Battery Day is technology we'd see at Giga Berlin. I'd love this to be a completely vertically integrated Roadrunner production line and cell-to-pack. He may have just been referring to cell-to-pack and plate cooling. Which Tesla vehicles will get which cells? It really depends on the factory. It looks like there will be 3 main cell chemistry families: high nickel, LFP, and Roadrunner. There are 4 vehicle factories complete or under construction, and at least 8 vehicles in production or planned for production. If I cover all the variables, this video would get very long and very boring very quickly. Here are the highlights. I'm sticking with my prediction that the Roadrunner batteries will be used for plaid versions of vehicles, and possibly the entire lineup of Model S and X. In the past, I said that the Tesla Semi might use cells from the new Roadrunner line. However, I've changed my mind on this. In the Q2 earnings call, Elon advised that the switch to lithium iron phosphate batteries in Giga Shanghai later this year will free up batteries for the Tesla Semi ramp. Currently, the cell lines at Giga Nevada are supplying batteries to Giga Shanghai. This implies that the Semi will use battery cells from Giga Nevada after the Giga Nevada cell lines are freed up. This means the Semi probably isn't using cells from the Roadrunner line, because the first Roadrunner line is at Fremont. In the Q2 earnings call, Elon also said that the Roadster will be built at Fremont, which makes sense because the Roadster will likely use the Roadrunner battery cells, and that's where the Roadrunner lines are. What about recycling? It'll be a few more years before significant volumes of automotive batteries come back to be scrapped and the materials recycled. Many of these batteries are finding second and third lives. However, battery recycling by J.B. Straubel's company, Redwood Materials, could prove to be very useful for Roadrunner. In a mature, full-scale commercial battery production line, around 10% of the cells can fail quality control or be scrapped. Pilot lines typically have worse scrap rates than established commercial processes. If Roadrunner is a true pilot line, depending on the line output, this could be hundreds of megawatt hours of scrap. If Redwood can recycle those batteries in a profitable way, it might ease the pain of high scrap rates and allow the line to become more profitable more quickly. Why isn't anyone else doing what Tesla is doing with batteries? In some cases, other manufacturers have already beaten Tesla to the punch in 1 or 2 areas, like single crystal cathode and cell-to-pack. However, 5 things give Tesla the ability to really knock it out of the park on Battery Day. 1. Tesla has the advantage of working from a clean slate to apply first principles with some of the best engineers in the world. 2. Tesla will be the only major cell manufacturer outside of Asia. Many of the best battery research labs in the world are in the US and Canada. These labs want to see Tesla succeed for the sake of the US battery industry. 3. Many battery technologies are developed in the US and Canada, but get shipped overseas because the US let manufacturing go by the wayside. Not this time. China tried to acquire Maxwell, but the deal was rejected by the US government and Tesla got the scoop. 4. Tesla is one of the world's largest battery consumers. This means Tesla gets first pick on about every battery advancement coming out of the US and Canada. Every startup wants to be the bride of Tesla. 5. This is a question for you. Would you rather strike a deal with GM or Tesla? Which company gives you more confidence to sign an EV-related contract with? What about mining? I don't think there's any way to scale at dozens of gigawatt hours per year without capturing some nickel or lithium mines for the sole purpose of feeding the Tesla beast. I don't think they need to get into processing those raw materials into battery-grade materials, but it's a possibility. What about competition? I don't see any other battery producers as competition for Tesla. They're an opportunity. Tesla can take the batteries from any supplier and weave them into gold with their superior in-house electronics, software, and engineering. In fact, in my mind, Tesla will be like a giant sponge, soaking up any excess cell capacity from any manufacturer that they can get their hands on. If an auto manufacturer hasn't built dedicated battery supply lines or their own battery factories, they'll automatically be out of the game. Tesla's platform is flexible. As long as a manufacturer can supply battery cells that meet Tesla's performance criteria and meet that criteria at low cost, it saves Tesla from the task of scaling themselves. Additionally, it will be about 2 years before Tesla really hits their stride with Roadrunner battery production. In the meantime, their battery needs will double from where they are now. This brings us to Giga Nevada. It makes sense for Tesla to keep scaling with Panasonic to supply batteries for the Model Y ramp as well as well into the future for energy storage. This will allow Tesla to focus their Roadrunner battery cells on the Cybertruck, Roadster, and compact vehicles for Europe and China. Earlier this year, I suggested that the Panasonic relationship would remain strong and that Giga Nevada would need to expand cell production by the end of the year. I received some pushback on this, but the prediction turned out to be correct and Panasonic is now installing another cell line. Combine this with my prediction that the Panasonic cells would hit a limit at around 300 watt-hours per kilogram, and I'm 2 for 2 at the moment. However, we still don't know if I was correct on the 300 watt-hours per kilogram for the right reasons. I'm looking for more clarity on this at Battery Day. How can Tesla just get into battery production if they've never done it before? Tesla has had a battery R&D facility for at least 5 and maybe 10 years. They have patents going back to the early 2010s for battery manufacturing equipment. They have an R&D line called Tera, which is likely the blueprint and proof of concept for the Roadrunner line currently under construction. Tesla didn't just get into batteries. They've been moving pieces around the chessboard for at least a decade to become the masters of their own destiny and accelerate the world's transition to sustainable energy. I expect that what Tesla unveils at Battery Day will bring Tesla to a new level. Not only will they be the masters of their own destiny and no longer completely dependent on other manufacturers, they'll be unrivaled in their ability to scale battery production. They'll be mass-producing battery mass production lines. And in the future, we might see a year where they install over 100 gigawatt-hours of capacity. If their lines can produce 13 gigawatt-hours of cells a year, which I still find hard to believe, 100 gigawatt-hours is entirely feasible if they're ramping production at 4 or 5 factories at once. Finally, I'm going to leave you with a moonshot idea. What if Tesla and CATL partnered on a Roadrunner LFP battery cell? If Roadrunner can reduce the cost of a battery pack based off a nickel chemistry from $110 to $88 per kilowatt hour, what could this do for an LFP battery pack that's already at $80 per kilowatt hour? Are you pumped about Battery Day? I clearly am, and I'll see you there on the day with a live stream. I'm looking forward to finding out where I was wrong, where I was right, and what Tesla has lined up that I didn't even consider. Let me know your thoughts in the comments below. If you enjoyed this video, please consider supporting me on Patreon with the link at the end of the video, or snag something off the merch shelf below. I'm also active on Twitter and Reddit. You can find the details of those in the description, and I look forward to hearing from you. A special thanks to William Gibson, Hugh Waller, Jacob Rasmussen, Nick Butler, and JJ Park for your generous support of the channel, and all the other patrons listed in the credits. I appreciate all of your support, and thanks for tuning in.